fortunate to have a returnee. Sarah Aciego is a graduate of Cornell University at UC Berkeley, BS from the first and PhD from the second. And it was essentially, I think it was right at 2 years ago, that we had the pleasure of having Sarah here. She talked about dust, which was a very memorable talk. Really, that was one that I remember very fondly. Actually, it was a great talk. And if you were here, I mean, when 40% of the not sediment load, but the nutrient load in the alpine environment. Basically, the alpine environment wouldn't make it without the stuff that flows in from China and other places. Maybe the Great Valley, some of it, but so I mean, it was really a neat talk. At any rate, so she was a member of the faculty of the University of Michigan at that point in time, had been for about 5 years. She has a long and impressive list of research publications, wide-ranging service in professional organizations, for example, the National Science Foundation, as well as an impressive array of awards and fellowships. She was a Packard Fellow in 2012, and if you don't know what that is, look it up. It's something that's very, very impressive to achieve. She is currently an adjunct professor at both the University of Michigan and the University of Wyoming. But in late 2015, her interest, and I'm pretty sure her passions, took her to at least some extent in a different direction, pretty much more away from the academic world than she was in Wisconsin at that time. And she co-founded Big Chill Adventures, which focuses on adventure travel and photography primarily to the Arctic, in particular Greenland, Iceland, and Alaska. Though their website also lists adventures in Yellowstone National Park and Panama as well. And her website states that she introduces small groups to glaciers, icebergs, dog sledding, and wildlife in week-long adventure travel tours. So that sounds pretty interesting. So you may well be able to understand her ability and interest in tonight's presentation and her topic, which is science, tourism, and citizen sciences. So I'd like to ask you to please join me in welcoming Sarah Aciego.
Thank you, John. So, thank you for welcoming me back. It's really a pleasure to be here again. I did have such a great time the last time I was here. It's one of the reasons why I immediately said yes to another invitation. I think you guys have a great community, and you ask, I shouldn't say surprisingly, but I've given a lot of talks in a lot of different places, and I was really impressed by the questions that I got the last time I was here. It was a lot of insight that you guys have into geology and kind of like Earth system cycles. So I am here kind of in a different hat, but I found when I was putting this talk together, I didn't want to talk about my adventure travel company. And what I want to talk about is opportunities that people have to participate in science, even though they might not be professional scientists. And in fact, that's kind of the history of science, right? Is that if you go back 2,000 years up to the present, it's only been in the last 100 years that science has been a profession rather than a hobby. And so what I'm going to show you are basically some case studies on how tourists and global explorers have participated in science and how they've participated in a really big way. So we can go ahead and get started. Where I wanted to start with this, though, is actually why I started to kind of formalize my ideas about citizen scientists. And it came from an interview I did a year ago, almost exactly a year ago, with The Street, which is the online Wall Street Journal spinoff. And so Mia Taylor called me and she said, I saw this article in the Smithsonian that said we should all go visit a glacier right now because they're all going to be gone in the next 15 years. But then when I talked to some other scientists, they said, that's a terrible idea. because all this travel is just going to speed up their demise due to carbon emissions, and we should basically just tell everybody to stay home. And I said, I did not say what I wanted to say, but I said, I think that's completely wrong. And I think that there's a responsible way to do travel, and that most people want to be responsible when they travel. They don't want to, litter the park or destroy the ecosystem. And in fact, that I think that scientists, and I'll pick on my fellow climate scientists, that I think it really does this public and society a disservice to dissuade people from going places where we are seeing active change. And this comes from both a long history of citizen scientists and then the projects that are going on right now. And so I'm going to kind of take you on a timeline of how citizen science has developed. But I want to first say why. I'm going to give you a case study of why. And we're going to be a little bit morbid here, and I apologize for that, but I want to get your attention. Okay? So this is a spatial distribution of fatal landslides that are recorded. Okay? So each dot represents a single landslide where there were multiple fatalities resulting directly from the landslide, not debris flows subsequently or floods subsequently, but this is a direct result of the landslide itself. And this particular study looked at a combination of why we started to see increasing fatalities from landslides. And it's basically looking at population density as a function of number per kilometers, square kilometers, right? So this makes sense. If you have a lot of landslides in an area and you have high population density in that area, then you're going to have more fatalities. Now, this seems actually kind of a simplistic kind of notion. It's one of those ideas that correlation doesn't necessarily mean causation. And so one of my colleagues in China actually wanted to look at this more carefully because China ends up being one of those countries that has the most fatalities. They end up having about 3,500 fatalities per year from landslides alone. So looking at causes of slope failure, I mean, this is something that you guys are probably familiar with the Great Slide in your backyard, right? So you have potential causes or contributing factors. You have bedding planes, right? You have a pretty steep slope. You might have deforestation or changes in vegetation. You've got some kind of fractures, excessive water that are going to help going in there. And then you obviously, at some point, you have some kind of trigger. It might be that you cut away underneath. It might be that there's an earthquake. But you have some kind of or excess rain that actually causes this to happen. And so, so my colleague, Dr. Wang, did this study, which he just submitted to the journal Geographic Science, looking at the history and correlation between different factors of landslides in China. And when I saw this, because I basically I helped him with English and helped him write the paper, this is a really striking figure. So this is number of casualties. This is greater than 100 in a single landslide. Okay, and it goes by county. And what you can see is that most of the country doesn't have these events, but there are certain counties where you have a lot of casualties associated with potentially one single landslide. And so he did a whole logistic regression analysis to kind of pick out which are the most important points. Looked at population density, and what you can see is, what you might think is that population density is the most important thing based on this previous slide. And what in fact you see is that's not, if you go on a county by county analysis, it's not the most important thing. And in fact, what he picked out as the two most important things is GDP growth. So it's basically how fast you're having development. So industry, potentially real estate development. And what you can see at these counties are pretty well correlated. But the other thing is a change in vegetation cover. So this is something that as earth scientists, we sometimes just kind of throw out there. You have deforestation, and this logically leads to landslides. And this is something that we see pretty frequently in the Pacific Northwest, right? But what I want to point out is that this analysis, the only data available that we can do this analysis with is only for the last 10 years. Okay, so Chinese, they're very careful people. They've been keeping records for 2,000 years. Why does it only go back 10 years? And the reason is that in terms of looking at something like vegetation cover, or if you were looking at changes in relief or even development, we don't have satellite observations that go back more than 30, 40 years, okay? So if we look at satellite data that you might want to do this kind of analysis with, where you actually want to say we went from trees to grass, that kind of analysis you can only go back to the 1990s, where you can actually discriminate between types of vegetation. If you go back to the 1970s, 1980s, you can, that satellite data, you can discriminate between rock and vegetation. And pretty much that's it, rock, soil, vegetation. So bare land versus vegetation. So you're pretty much limited in that kind of analysis. And then pre-1970s, there's nothing, right? You might get some aerial photos, but there wasn't this kind of idea of looking at things from space. So like I said before, causation, correlation, are these things the same? And so a lot of work in the last, I would say, 30 years in earth science, when we're trying to get longer records, has been to go back to tourist photos. And so I'm going to show you this kind of, it's a result that I kind of put together from this based on this, this paper and then a paper that was published about 10 years ago. So this is just submitted, it's not out yet. And what I want to do is look at this area right here, which is the Yunnan province in southwestern China. And so in the late 1800s, early 1900s, there's this huge wave of tourism into China. This included just normal tourists, foreign aid workers, and religious missionaries, it's pre-war tourism. And the Nature Conservancy actually has been scanning these photographs and sending people back to the exact same location where the photographs were taken to try and get a handle on changes in land cover. And so this is a photo taken from a tourist in 1936 of one location here in Yunnan province, which is right here in southwestern China. And what you can see is that in this time period between 1936 and 2003, there's actually been an increase in vegetation cover and reforestation in this area. And the same thing here, photo taken in 1923 compared to 2003, and you can actually see that there's been a fair amount of abandonment of terrace farming and reforestation of the hills here. And after going through about 500 photos, what Mosley found was that forest cover has not changed very much in the last 100 years. And in fact, any change at all would have indicated that there's a more stable forest ecosystem there. So in this place where you're seeing this really high number of landslide fatalities, which seem to be correlated in the last 10 years at least with a vegetation cover, would actually not be accurate for going back further in time. And so this suggests that, suggests that there's a value to actually going back and looking at old tourist photos to provide additional information. And so I'm going to give you another example of some great tourist photos being valuable. And that is up in Alaska. So similar to this vast wave of tourists and religious missionaries going to China, there was a similar kind of wave of tourists going to Alaska in the early 1900s, late 1800s. And they were going on these steamships, not the cruises that you see today, right? So they're pretty intrepid travelers. So there's these whole series of photos, which have actually been put together by a couple of the National Archives, and which were recently assessed by the USGS up in Alaska. And one of the reasons that I think it's important to talk about these glaciers, I mean, it seems a little bit trivial, right? To be like, okay, we know the glaciers in Alaska are shrinking, but it's not trivial. And the reason is that I did a lot of work in the Arctic, in the Antarctic, as a professor and scientist, and for sure they're important. It's 300 feet of sea level rise, if they go away. But that's not going to happen in our lifetime. What's going to happen in our lifetime are all of these small glaciers are incredibly important, and they're only going to become more important when we think about water resources. So the Glaciers in the Wind River Range, I talked about a little bit the last time I was here because my whole talk on dust was a record from the Upper Greenland Glacier. But I'm not sure if you guys are aware, but the Wind River Range glaciers account for 20% of the base flow coming out of Green River. So these are incredibly important for water resources in Wyoming. If we look at the glaciers in Bolivia and Central America, they account for something like 40 to 60% of the drinking water in these populations. And there's a huge divide in the Karakoram and Himalaya in terms of these glaciers that it's like something like 1/6 of the population depends on water coming through the rivers that's directly coming from glacial mount. And of course, glaciers are incredibly important as opposed to precipitation or snowmelt because they act as a natural reservoir. So as a reservoir of ice, they actually sublimate slower than what you would have as evaporation from precipitation. And so if you built a reservoir, it would actually lose way more water per year than you lose from a glacier, given the same temperature and humidity conditions. So these are all really important glaciers to study, and people are always talking about collecting ice cores. Yes, everybody agrees they're really important. And one of the ways that we assess at the health of these glaciers is to actually look at something called the AAR, which is a ratio between their accumulation area and their ablation area. Glaciers move under their own weight, where you have snow that turns into ice that flows downhill, essentially. And as it moves below this equilibrium line, it loses mass either due to melting or sublimation, or iceberg calving. And a glacier that's in equilibrium, so it's stable, it's happy, basically the accumulation equals the ablation. If you have more accumulation than ablation, so you have a particularly long couple of winters like you guys did here, maybe you start to accumulate more snow, and the glacier will actually start to advance. So the tongue will start to actually move forward. And if the opposite is true, where you actually start melting or sublimating or calving more than you accumulate, then you're going to recede. And the retreat is not actually the glacier moving back, it's just melting a lot faster than it can keep up in flow going downhill. And so like I said, the way that we assess this balance between accumulation and ablation is that we measure the area of the accumulation zone and compare that to the total area of the whole glacier. And that ratio is called the AAR. Something like a 50 to 60% AAR would be considered a stable and healthy glacier. And what you want to do is be able to monitor that over decades in order to see, is this something that you're seeing like a stochastic kind of change, or is this something that's you actually have a long-term decline? For alpine glaciers, this is particularly problematic, and I want to tell you why by talking about Antarctic glaciers. So glaciers in Antarctica are so different from alpine glaciers because they move so slow. They're like the sloths of the ice world, right? So an Antarctic glacier may move something like a half a meter a year, right? This is like, and this particular glacier is 60 miles long, okay? It doesn't move very fast. And this glacier here, the Taylor Glacier in Antarctica, it's not retreating or advancing. It's been stable at 55% for basically as long as we've been measuring for about 30 years. But like I said, we want a long record of retreat and advance to determine the health of this glacier. For a glacier that's moving really slow, this is actually really easy to do. So I'm going to tell you a little bit more about this glacier. It's in East Antarctica. It's one of the glaciers draining the ice sheet, the East Antarctic ice sheet. The accumulation area is actually Taylor Dome. This is really well studied. And the ablation area is the glacier itself. And so 10 years ago now, we went there and we collected samples on the surface of the ice the whole way down the glacier. And on our hands and knees. And no joke, I have pictures of it. Because we need to get a really high resolution record because we're going to compare the stable isotopes of the surface ice to the accumulation area. And when we did that, what we were able to see is that the surface at the very toe of the Taylor Glacier was 70,000 years old ice, and up here at Windy Gully here, it was something like 10,000 years old. So when we made this record, we were then able to compare it to its accumulation area, and in doing that, we can see how long we know how long the ice has traveled to get where it is, and we can actually see, okay, this glacier is actually really healthy. It hasn't moved very differently over the last 70,000 years, okay? So it's stable, it has an AAR of 55%, okay? So that's really great. Now, the problem is if you look at an alpine glacier, if you wanted to do the same thing, alpine glaciers, they might be 300 years old. So we're able to measure the age of this ice by looking at the oxygen and hydrogen. It's really different here versus here. But you get up to the alpine glaciers and there's almost no change, and it's really high frequency. So you can't actually do the peak matching that allows you to see how the ice has moved through time, okay? So the only way we can do it is actually observe it from the outside. And so I'm going to go back to these photos, and I'm going to show you how things, these are qualitative measurements, okay? Not quantitative. I'm going to give you a quantitative study. So these are qualitative measurements of glacial retreat in Alaska. So this is a photograph, the one I showed you earlier, was taken by G. Hazard, who was a passenger, one of the only, camera carrying, I guess there must have been at least 3 of them, so this is one here and the guy taking the photo. Camera carrying passenger on a steamer that visited Glacier Bay in the mid-1880s. Okay, so this is one of the earliest photos of this area. At the time, I'm actually able to use this photo to measure the thickness of the ice here. And you can see it's about 100-meter high cliff face. And they can tell essentially the size of the icebergs that were coming in, which has important, they're important measurements for figuring out how fast things are basically inflating. And then there's this photo taken in 2005, exact same spot. There's a 26-mile retreat, and the glacier used to be a single glacier. It's now retreated into 2 glaciers. And what you can see is also, you can see the other side of the bay where there's kind of this abundant vegetation. So a qualitative measurement of kind of an extreme glacier retreat. Now, this is something that we observe pretty much worldwide, right? This is something you guys probably all know, that most glaciers in the world are retreating. But there are, in fact, about 10 to 20% of glaciers that are advancing, and it's not something that we understand very well. And this is a good example of one that we don't understand very well, which is why this was a really important photograph to find. So this was a photograph taken by tourists to Field in 1941. And what you can see is from the vantage point where the photo was taken, it's about half a mile to the face of the glacier. And what you can see is also all this rock here is all bare, okay? If you look in this photo, what you see is the glacier is actually advanced about a quarter of a mile, and it's also extensively thickened, probably about 30 to 40 feet. And on top of that, we have evidence in this photo, and comparing to this photo, that there's a large deposition of moraine material, right? So this would indicate that not only did this glacier has advanced, but it actually advanced further, probably to the photography spot in this time period, and then has since retreated back to where it is. So when we're talking about how different glaciers are behaving under climate change, or whether it be natural or man-made climate change, these kinds of measurements are really important to kind of point to the statistics of how glaciers are changing. So I actually put this next study in here for someone in the audience who I went to dinner with the last time. So there's this really cool study that just came out looking at the Easton Glacier on Mount Baker. So the so this is a 25-year study of looking at the health of this glacier. And this was these photos were taken by the scientists, so they've been going there for the last 25 years. Actually, this photo was taken by a climber. And one of the reasons they chose this spot was because they had this photo. So they're actually able to go back to the same spot and measure it. And so they chose a spot and actually were able to put the record even further back based on notes and letters with climbers who had climbed Mount Baker in the 1970s and 1980s, as someone in this audience did. So, and this is actually the result. And I want to point out, so a couple things. So this is that AAR ratio, right? So like I said, you want it to be stable, and you want it to be above 50 to 60%. And what you can see is that for a long time, actually, these were measurements taken from the 1990s and early 2000s. The glacier was in a state of decline, but it was above 50%. And in the last, basically 10 years, it's dropped below 50% in terms of AAR. So it's retreating relatively rapidly now. And then this is a satellite image of that retreat. But what I want to point out is that these measurements up here, which are incredibly important for setting the whole trend, would be our measurements from peak climbers, essentially, so tourists going there and actually saying, like, this is where the glacier was, this is where we went on, and talking to the scientists about where they were at that time. Okay, so now I'm going to switch gears, and talk to you about introduce you to some projects that you could be involved in. So this one is really cool. This is actually a project that was started. This is looking at sea ice in the Arctic, and this was started as a series of science expeditions and some cruise scientists for cruise ships said, hey, we want to be involved in your science too. So this is up in north of Canada, very close to the North Pole. And what you can see is these are all melt pools, actually. The ice here is probably about 2 to 3 meters thick. It's not dangerous at all to walk on it. It looks dangerous from here. You're like, oh, they're just going to fall right through. But these melt pools and the state of sea ice is incredibly important to measure on the ground. And I'm going to show you why when we look at this. These are satellite images or measurements of sea ice thickness and sea ice extent for 2010 to 2013. We won't talk about the last year, it was tragic. So I'm just showing you the from about 5 years ago. So what you can see is that it's variable, right? Which is actually what you would expect, right? That as you have different winters, you might have more snow, that snow turns into ice. It's cold enough that you start freezing from the sea ice itself. And you can see some really cool features that show up where you see really thick ice, something like 3 to 4 meters thick ice showing up in northern Canada and northern Greenland. Pretty thin ice here north of Alaska. And the problem with satellite data for sea ice is actually completely unresolved. So we show these images, and it's really good for extent, but it's actually really terrible for ice thickness. The errors on this can be anywhere from 50 to 100%. So I'm showing you something where you're seeing like this huge range in ice thickness, but the errors can be really large because of those melt pools and because you have snow versus ice on the surface. So you have 3 different surfaces, and they scatter the signal coming from the satellite very differently. Okay, and so in order to they actually have to calibrate those measurements every year based on what the surface is. So they need people on the ground actually taking measurements of what the surface of the sea ice is. And also to kind of confirm the thickness just so that the model all works out. So there's this international collaboration of science expeditions. So these would be Russia, China, the Japanese, and the Americans put together this program called Ice Watch, which coordinates and then they collect and archive all these visual sea ice observations, and they have a protocol for it. And you can actually go online and see it's called the ASSIST program, which records everything exactly the same. So it's like completely standardized, everybody can go in and use it. And it's just a great international project. Anyway, so like I said, these onboard geologists for cruise ship were like, hey, we want our cruise people to be able to do this too. And so So these here, this is a Danish expedition, this is a Canadian expedition, this is a RV Lance, that sounds American, right? American expedition, and then we've got a couple more Danish expeditions down here. This one right here is actually a cruise ship sailing the Poseidon, it's a Poseidon Adventures, basically. So this crew actually went out and they took 41 measurements of sea ice. And you can actually go here to the website and they've got 2015, 2016, 2017 that data. And they've measured old ice, other ice, first year ice, new ice in these tracks across the Arctic Circle. These are the actual passengers who wanted to take part in this science. And they're measuring the salinity of the water here. They're measuring the temperature of the water. They actually cored here. And then the other thing that they did is the ship put a camera up on the mast and they took observations of these melt pools. And the reason that they did this is a really interesting scientific question, which is, why do you even have melt pools, okay? So if you look at sea ice, this is an image of a core of sea ice. I'm trying to get this out of the way. I don't know why that arrow is up there, but so they took a core of sea ice and they put some dye in it, and what you can see is the dye is running right through the inside of the core, okay? So this ice is filled with brine channels, okay? Because what happens when the sea ice forms is that it's freezing pure water, which leaves behind this really saline solution, which then has a much lower freezing temperature, right? So you have these channels that are forming, and the question is, why would you have water pooling on the top? It should just drain right through, okay? And so this kind of question was unanswered until this year, 2017. It was a fundamental question in sea ice science, okay? And so this is a colleague of mine, Polashinsky. He wrote this paper and he showed his tracks for the expedition that they did with the RV Lance. And then he also took that data, the photos of where you had melt pools, and he did this basically a time series of where do you have melt pools, the brine, and the temperatures. And he came up with this model for what happens with melt pools. So in the winter, so it's dark out, in the winter you have snow falling on the surface, you've got these brine channels that keep water flowing down into the sea, right? Starts to get sunny out, the snow cover is still there, so it's basically insulating these brine channels, so you still have water flowing through. And at this time, the ice itself is getting a little bit warmer just because it's from the solar radiation. Melt pools form because as soon as you get a little bit of fresh water, so melting of that snow, what ends up happening is the snow that fresh water starts to flow through the ice, but it's not saline. So it immediately freezes. And so you form these melt pools, and it also shows why you have catastrophic draining. Okay, so you get a little bit warmer, the ice warms up a little bit more, and then the channels form again, and you basically dump out all that fresh water to the seawater below. So this is a model that would not have been developed if it hadn't been for all of these amazing observations by people on a cruise ship going across the Atlantic. So, but a lot of people don't want to go cold places. So I call them fair weather citizen scientists. So I chose, that one was really cool because it's so recent, it's 2017. And I also tried to choose one that had some recent results for fair weather scientists. But this program has actually been around for about 30 years, and it's absolutely amazing. So Reef Check it's an international consortium, much like that the Sea Ice Project, where it's a voluntary collaboration, okay? And the voluntary collaboration is the same thing where they have a standardized way of measuring reefs. So they take out a grid. Everybody that participates in the program is using the same set of standardized measurements to take the observations. And these groups actually, you have to be a scuba diver already. So they're not going to train you to scuba dive. But a lot of people I know are actually, they're adventure travelers. They want to go to these cool places. They're divers. And they also want to be a part of protecting something that they enjoy visiting, right? Or at least understanding their chosen vacation spot. So this reef check organization, you can choose any one of the international ones to get trained at, and then you can actually deploy at any of the other ones. But they'll train you, it takes about a day. There are more than 90 countries and territories that are participating in this. So basically every diving destination you can think of. So the Great Barrier Reef, Fiji, Hawaii, the California coast. And so like I said, they have, and you can do it even if you're not a diver, if you're a good swimmer, you're a good snorkeler, so you're a good swimmer. You can also do it that way, so from the surface. So they'll deploy you with a camera, your grid, and they might actually, they have basically it's a color chart to look at what the reef color looks like for bleaching experiments. And the program has been incredibly successful for two reasons. One is that they, over this last 30 years, I would say probably 40 of those 50 plus publications have been just looking at populations of fish and just saying what are the species, relative species, maybe they may or may not have changed over time, but they basically built the database, right? So this would be completely impossible from any one organization to build a global database of these species. But more recently, they've actually been really important in starting to do monitoring, and the same thing again where you're ground truthing the satellite data. And what you can see, I'm going to show you, is the satellites are doing a really poor job. So it's really important that people are still doing this. So this was a study done on the Great Barrier Reef. These are the Landsat 7 ETM images of the Great Barrier Reef, and they try to choose different, basically wavelengths to distinguish between sand, rock, algae, coral, and then different kinds of coral. And so the number of sites here is the number of sites that have been looked at by Reef Watch. So it might be something like 50, or it could be something like 200. So there's a lot of places that are relatively close to shore, or maybe they're beginner dives that people can do without being too technical. And in this case, 800 of particular reefs. So, and what you can see is these numbers here are the accuracy of the satellite monitoring. So we're still a ways away from being able to do this without boots on the ground or fins in the water. The other study that just came out this past year is also really cool, and it looked at this mass die-off in Indonesia. So there was a bunch of Reef Watch people that were doing diving on Bunaken Island in Indonesia, and these are their sites that they went to. This is a satellite image, and you can actually see how they gridded the sites. They put this marker on it, and then they look at the relative mortality of this particular reef. And because they have this long record of having been to these 4 sites over the last 20 years or so, they can actually say exactly when this happened, this mass die-off. And the mass die-off actually happened right after this rapid sea level fall following the El Nino this past year. So we were getting hammered with water. It all came from the West Pacific. So, all this water moved out of the Western Pacific, and sea level dropped, and then you had this mass die-off. You had something like a 40 to 70% mortality rate for this reef. Okay. By the end of this talk, you guys are thinking I'm just going to keep bashing on satellite measurements. We're just trying to make them better. So this is so the last 2 projects I want to talk about are actually they're really new. So there's actually almost no data, but the app for your phone, which you can turn on now and download them, I don't mind. They're real-time uploads to a pretty extensive database. And so I think that they're worthwhile for people who don't want to scuba dive or go into the Arctic to take sea ice measurements. These are things that you can do. So I know a lot of people that are going to Hawaii this year. And In Hawaii in particular, but also the west coast of California, you have something called a king tide, which is it's a non-scientific term, and so you will see it on the news a lot, like, oh, killer king tide, everybody stay out of the way. And it's just a term that describes exceptionally high tides. And the reason that you get these exceptionally high tides are because of the interaction between, our tide from the moon and when the new moon actually lines up with the sun. So you get an extra strong high tide when you actually have the sun and the moon aligned gravitationally pulling all that water in that direction. They tend to be highest, you tend to get these king tides mostly at lower latitudes. You don't tend to get them at higher latitudes, so you see them a lot like in these island nations. And as I say here, they're accurately predictable in timing, but not necessarily in magnitude. And so we can do some observations of the king tide. So this is the king tide. So the season is in Hawaii is from about April to July for these king tides. And this is showing a sea surface anomaly in feet. So this is almost a foot higher water coming across Hawaii, okay? So we can see this, but the question is, as we're having an increase in sea level, in addition to having a king tide, we're at a loss as to how to predict the impacts on infrastructure, or even how big the king tide is. And so what I'm showing you here is the news from about a month and a half ago, Big Island News. This is the king tide alert. It's got no shape to it whatsoever. It's not higher in Kona versus Hilo because we don't know, right? It's really hard to predict what the magnitude is going to be in different locations. And so all they can say is basically anyone on the coast, you might have flooding. And this is kind of that same kind of simplistic view of this is king tides, you might reach shore, El Nino higher, coastal storms, you get big flooding. So we just don't know enough about what the impact is on infrastructure. And so this program just started, I think it's about a year and a half ago now. It's a sea grant in collaboration with the University of Hawaii. And locals have actually been participating a lot in this. There's a couple of thousand observations at this point. But you can do it as a tourist. There's an app. You basically register online with the username and you send in upload data, download the app, and then you use your phone, which has a GPS on it. You take a photo of the beach, where it doesn't even have to be at the king tide. They're basically just trying to track what tidal motion is as it relates to the predictions. And you take that photo and you press submit, and that's it, it's done. You've participated in a cloud-based, gigantic scientific project. And these are typical photos. Isn't this crazy? This is just a normal king tide at the U-Haul place. And the truck is like halfway underwater. So this is this particular beach flooding, predicted beach flooding right here. And then this one too. So basically it's coming right up to the guide station. So yeah, so this is something that you can easily participate in if you go to Hawaii. I don't think that there's a project that's just started in Northern California doing the same kind of thing where they're trying to get tourists to start participating in, basically it's a gauging problem, right? It's like, what are the levels at certain times?
What's the difference between the dotted purple and the solid purple?
So they are, my recollection is that it is basically an error ellipse. So this would be the maximum and this would be the minimum. Observed, right? So I know what it is. This is the predicted and this is the observed. Sorry, not paying attention. So yeah, so the observed ended up being much higher than the prediction through this time period. Okay. So, but I'm talking to geologists. So this is my favorite citizen sciences project, and I actually use this on the trips that I go on with my clients now. Let's talk about some geology. So what John didn't say is I'm also a pilot now. So in the last 2 years I got my pilot's license and I have a commercial. I'm going to start teaching soon. And so I actually really liked this picture because I didn't take this picture because obviously this is 10 years ago, but I have been flying in Iceland the last couple times I've been, and it's amazing. So this is the Eyjafjall eruption in 2010. I don't know where you guys were at this time, but this was when I was doing a postdoc in Switzerland, and I was about to move back to the United States. And I was giving a talk in Rome. And what you can see is I got stuck in Rome for a week because this ash cloud came over and this was all the grounded, basically everything was grounded. So people could fly here, they couldn't fly here. And this went on for about they were grounded for about 2 weeks, flights getting close to Iceland. But the eruption went on for quite some time. And what you can see here is that the ash cloud moved over Norway, moved over the UK, and it changed pretty significantly with time due to differences in the atmospheric circulation. So you just have variations in the jet stream, you might have a high pressure, low pressure system, and all of a sudden this ash moves around. So ash is really close to dust, which is very close to my heart. And the reason it's close to my heart is because ash, like dust, has incredible amount of nutrients in it. And it turns out that it fertilizes the oceans like crazy. There's a project that I am still on, looking at the evolution of coral 400 million years ago based on volcanic ash deposition, right? So you fertilize enough, you get enough nutrients in the ocean, you can actually change how species are evolving. And so it drives biogeochemical cycles, and then because you're a geologist, you should all know this, it's also probably the most important dating technique for the sedimentary record. So the PT boundary, which you guys are going to hear about soon, is all about that ash layers and actually being able to date ash layers pretty precisely. So the interesting thing about this is that despite the fact that we've been observing volcanic eruptions for quite some time, we see ash in the sedimentary record and the ice core records. We actually have not collected very much ash in situ and correlated it with atmospheric transport. And this ends up being kind of important because ash has a variety of grain sizes. So you can have really fine ash, you have coarse ash, and how it falls out in that process will change depending on atmospheric circulation. So the British Geological Survey, this eruption is going on over a couple months, and they're thinking, oh, we'd really like to collect some ash. There's a limited number of us. We're not going to go to 1,000 sites all over Europe, but maybe we can get some people to collect some ash for us. And so this actually drove them, it's amazing. They developed this app like right away. And they have people, they partnered with the Smithsonian. That didn't happen right away, but now part of the app is that. And there's a worldwide database of volcano information, which is all geolocated. So you can get on your phone and you're like, where am I? My closest volcano is Yellowstone. Tell me about Yellowstone. Who's monitoring it? What are the ash layers in the area? But then you can also, for Iceland, this is one of my clients' photos. She was curious about a particular volcano that we were next to. So a screenshot. And you can see, you guys that are going to Iceland, it's amazing. There's so much cool information about the different eruptions that is available on this. But in terms of citizen science, it's turned out to be a gold mine for volcanologists. Because what you can do is, if you're lazy, which I advocate for, is you can just take a photo of something that hasn't been photographed before, a particular fissure, or maybe you found some amazing giant fist-sized algae behind the shell in Kona, which I have before. Take a picture of it and you can upload it to this site, and it adds to this database, which is used, if you Google Scholar, this database, the one through the Smithsonian, thousands of publications. And people they're daily going through and getting more information from this. They'll have information about the type of volcano, whatever. Okay, so if you're lazy, you set your location, you You can just enter a description. That's fine too. Take a photo. The photo is geolocated, which is cool. If you're in Europe, you can actually set it up and collect an ash sample, and you can send it in and they'll analyze it. And then that geochemical data will be part of this global data set. And that's why you have, if you look over here in this corner, this right here, all of these gray dots, these are user uploaded data points. Something like 500 at this point, but most of them are in the UK because the British Geological Survey put a call out to their community and said, please collect ash. Tell us what you see, what it looks like, and send it in. And so that's what this is, and it's free. I mean, you have to pay for the shipping, but or you can just do it. Okay. So this is an amazing collaboration, and I think there have been. I haven't talked about the failures, but science is iterative. There's been a fair number of failed apps, right? Citizen scientist apps to look at different things. The reason that this one has been so successful, this is 7 years old now, is because it leverages a database that already exists, right? So this is the Smithsonian database. It's got something like 5,000 to 10,000 entries already with all this information. And so it's really easy to take part in it. Whether or not one person takes a measurement does not affect the veracity of the rest of the data, right? Okay. So, I love this picture. It was funny because I was putting this together. I was like, "What's the future?" These two last projects, the ones I just presented, I think they're kind of the future. It's where we're at right now and what's going to go forward. There's no publications from yet because we're still getting started. But there are a couple things that are kind of on the horizon. One is something I kind of already talked about, is just the idea of like streamlining data collection and improving management, automating quality control, so making sure that all the measurements that are getting taken are the same way, and expediting communication. That's from 5 years ago. That was the future event. So we're kind of there. This guy, Shah Shelby, it's funny, I tried to get something from his website to show you because I saw him give a TED Talk, but he's still kind of like at the patent stage. But he's a National Geographic explorer, and his company, which is a nonprofit because he doesn't want to profit from this, is to design sensors like geophones for earthquakes, for deploying on glaciers, pH meters, flow meters, that you can basically, he gives you the template for it, and you don't need to be an engineer to go to the hardware store, put things together, and plug it into your iPhone and take other kinds of measurements, like quantitative measurements, without sending anything in. He also developed a prototype for a flow meter. That's what I was trying to show you, but I can't find it. He doesn't want to show it yet. Flow meter, where you can print it on a 3D printer. So these 3D printers are now carbon fiber. You can use things that are completely submersible, and then you could actually plug that in and take it with you anytime. So I'm just going to end. It's running a little bit long, but I'm going to end with this really cool story. Okay, so I couldn't memorize this because it's just too much information. But I also wanted to say that I like to travel. I know a lot of people like to travel, but maybe you can't travel. Or maybe you just got back from vacation and you're thinking, well, I need a year. There is amazing projects that if you want to do some cool research, you can do, and it gets used. So I'm going to give you an example of one. This is a project from, it's called Zoolympia, and they're like an overhead for a whole bunch of different citizen science projects. This is probably the most successful of them. It's called the Old Weather Project. And the Old Weather Project is 400 years of ship logs that cannot be read by computers because the script is, a guy 400 years ago in a super slanty cursive. No computer recognition is going to do it. So what they've done is they've scanned all these ship logs in, and you can go in and you can translate a page, you can translate 10 pages. They have translated in the last 20 years about 1 million pages. That's why I said it's the most successful. And they've had some really amazing results. They've looked at weather systems during battles to explain why you had sinking of ships that should not have sunk during battle. Where they've looked at high-low pressure systems, El Nino across the Pacific 300 years ago, these kinds of things. And so I just wanted to share a story of one of the projects, which for those of you who are going to Iceland will appreciate. So this is the sinking of the Jeanette. The Jeanette was built in Wales. After 10 years of service, she was sold, renamed the USS Jeanette, and was moved to San Francisco, where on the 8th of July, 1879, she set sail under the command of Lieutenant George Washington DeLong to claim the North Pole for the United States. 2 months after her departure, the Jeanette became stuck in pack ice off Herald Island. She drifted with ice for almost 2 years. This was not intended. This is not the Fram. She drifted for almost 2 years between 65 degrees and 70 degrees magnetic latitude before the crew was forced to abandon the ship when the pack ice crushed and destroyed the ship in June 1881. The crew then embarked on a 1,000-kilometer, 4-month trek across ice and open water with dog sledges and 3 boats full of supplies. It was a horrible journey. Many people died. The captain, in one of his last acts, in an attempt to preserve the ship's logbooks, journals, and charts, would move them to higher ground to save them from spring floods when they reached ground. Shortly afterwards, he died. Against all odds, having been left there at the journal for a long time before it was recovered, it actually survived, and it's in the U.S. National Archives. Old weather volunteers transcribed the complete set of logbooks. In doing so, they started noticing that there were fairly frequent and tedious notes of the aurora that were taken. Next page. Okay. So at that time, now, looking back, the only records of historical geomagnetic activity that go back that far is the AA indexes, which is kind of it's a general index of magnetic activity. It doesn't tell you anything about intensity. And the only observations they had of that kind of general, what might cause aurora, were from sunspot observations from the Royal Observatory in Greenwich. So these logbooks, they actually took them nightly, basically. And so there's this chart where there's well over 100 observations of the aurora, and they documented the intensity, the colors, the timing, where they actually saw them, if it was a halo versus stripes. And I'm just going to skip to this right now. Wow. So this, okay, so they documented the spectrum, rainbow versus prismatic versus different, if there was red, green, yellow, white, purple. And it turns out that these are good proxies. I don't know what you know about the aurora, but they're good proxies for what the particles are interacting with and what their velocity is coming into the atmosphere. So if you see, let's see, red, this is usually about 250 kilometers in the atmosphere, caused by atomic oxygen with a single D energetic wave. So you have all the different electron levels. So this is the D1 level. If you see green, this is usually S level for oxygen. Nitrogen tends to emit in blue and red, which leads to the purple. So you have nitrogen and oxygen basically emitting in the atmosphere. White actually tends to usually get because the eye can't actually perceive the colors. And so oftentimes photographs like this, the camera does a better job of distinguishing those colors than the human eye can. So I was here for both of these pictures, and this one was intensely green, really intensely green, and then this one was more white, and it was only in the photograph that the purples and reds came out. And so it turns out that while the colors were not always recorded, there was a group of observations associated with multiple descriptions of color. So we're looking at different charged particle velocities interacting with oxygen and nitrogen. So the fact that you have multiple means that you have a whole bunch of different velocities coming in of solar charged particles. Coincided, so between November 1880 and March 1881, those time periods perfectly coincided with large sunspot groups that were observed at the Royal Observatory. So this was a way of actually confirming, 130 years ago, that you had the same kind of phenomena and what the linkage was. They got a whole bunch of other data about the relationship with the moon and the magnetic field with this as well, but that was a big one. They were able to identify the beginning and end of the auroral seasons, and like I said, the effect of the lunar phase on the aurora. So I thought it's pretty amazing what a little bit of curiosity will get you, even if you're not doing it as a profession. So this is me trying to explain how glacier works. With the only whiteboard I had. All right.
Questions for Sarah?
You said about 10% of the glaciers around the world, globe, are actually increasing in that higher aging arc. Have you mapped those out?
Yeah, so I can actually, there's some in Alaska, not a ton, but the biggest dichotomy is actually here. There's a east-west transect here in the Karakoram. So this area, so I should say this area, there's a lot of ice here, more ice here than anywhere else on the planet outside of Antarctica and Greenland. Within the community called the third pole because there's so much ice there. And so that kind of 5 to 10% number is swayed by this. And there's an east-west divide here for the glaciers that are facing east versus west. And it's not exactly clear why, because it's not a solar incident thing. It's not really clear. This is definitely active research at this point. So they're stable or advancing.
You mentioned this interesting deviation of receding glaciers versus advancing glaciers. Are there, aside from politics, what would explain, assuming that some of the commentators are actually honest, but they're coming with a straight face that the glaciers are not disappearing, and others say, of course, that they are.
Yeah. So
what caused this misunderstanding?
So I think that they're, leaving politics aside, so one of the hard things about being glaciologists in climate science is that there's a lot more nuance than we're allowed to say. Not allowed, but if you're asked in an interview in 5 seconds to yes or no, you have to come up with an answer really fast. And the nuance here is, and what everybody jumps on is, well, this would happen anyway, right? And the nuance is, yeah, it kind of would, because, well, they were retreating anyway because they had advanced during the Little Ice Age, right? And so that's the nuance, is that they were already, you might have seen these giant moraines, either in the Wind River Range or, the Teton Glacier here. They came from that advance and then that retreat. What's happening now is a little bit different, right? So you had that retreat coming out of the Little Ice Age, and then depending on where you are, maybe they would have disappeared anyway. But the reality is that most of these glaciers, right, when we're looking at mid-latitude glaciers, they're really close to the freezing point all the time. So it doesn't take very much in terms of a half a degree to get you to the point of receding quite tremendously. I don't know why someone says an observation is wrong. That seems like more of a psychology question than a science question. That honestly, because it's really easy to say, well, winter wasn't that cold, or winter was really cold. You know, I'd rather actually use something that you can measure to show it, and you should be able to observe. It should be easy enough to observe. But I think what ends up happening is that for the small glaciers, they're complex. You know, there's a lot of reasons that they form. There's the east-west divide in the wind-river range in terms of which ones are doing well versus not doing well. And you also have the problem that it's not always temperature, right? Or not straight up temperature, right? Where you have dust and ash and soot, black carbon on the surface, which is absorbing more solar radiation. So it might be at -10, but it's still melting. It's, well, how does that happen? Well, let me explain it to you, right? Mm-hmm. So I think it's the nuance that gets lost, and then without the nuance, it's easy to say that there's disagreement. I don't know if that makes sense.
I think it makes a lot of sense.
Yeah.
We're talking about so many competing factors.
Yeah.
But the simple answers that we see in most of the major media are too simple.
Right, yeah, exactly. And I think, one of the important things about, the glaciers are near and dear to my heart, is that if the glaciers were retreating anyway, you still have to deal with the issue that there's going to be a water crisis, right?
It doesn't go away.
It doesn't go away, right? And so understanding what they're doing and monitoring them is important in the fact that there is a large population that is dependent on them. Yeah.
Actually, this is fascinating. There's many other disciplines where we're finding that high technology has a lot of variation, like you're showing, not just with your satellite, but you're finding that in many other disciplines. And yet we have the capability of collecting observations which are real.
Yeah.
The key is how do you organize this thing of citizen glaciologists in medicine? How do you organize that to really? I think this is a powerful tool.
Yeah. Well, I think it goes back to what I was saying about why, like my volcano app has been successful when many others hadn't. Is that and it took them a long time. There's a fair amount of literature actually where the Smithsonian has told it we had to update the database. It's going to be down for 2 months because big data is big data. There's a lot of data there, right? And it's not just that the data that's there, it's the communicating with the data requires a lot of bandwidth, right? So people uploading and downloading that amount of data and processing that data, right? And so you need to have the capability of leveraging infrastructure for that data. And I think that's why a lot of them have failed. And I don't want to pick on anybody, but so Shelby is doing this amazing work, and I really wanted to show this project that is going on right now. And I actually could probably bring up the link. Do you guys have Wi-Fi in here?
We do.
Let me see if I can show you guys, because it was intended to be really incredible. Don't look at my search history. Over the.
So there's an auditorium. You should be able to.
Yeah, I just got it.
Accept.
Yeah, I just got it.
Okay.
So it's called Over the. All right, I can't show you. I will send him the link and he can show you. It's this project that they did to deploy. They actually deployed this team of researchers plus some tourists that were going into Africa. And the idea was they were going to look at species of birds and fish and mammals and all this stuff in real time, linked up to which the idea was supposed to be that it was going to turn into a way to show the future, right, of dealing with big data in real time. And it turned out that it didn't work. So they did a journal every day, and you could see where they were every day, but you couldn't see all the extra stuff. So they were supposed to be doing like pH of the water, temperature of the water, photos of the animals, and it was the bandwidth. They couldn't deal with the bandwidth. They couldn't deal with the database linkage, and we're not there yet. That's it. I'm agreeing with you. We're not there yet. It's a real problem. So.
But that's one thing that technology can address is,
Right.
is the bandwidth. That's
Yeah.
the whole.
Yeah, exactly. And I think ground truthing is so important. I mean, like having people take a measurement that we know this anyway, but it's so important.
With the king tide business, doesn't the Coast Guard and maybe the Weather Service measure an awful lot about the tides on a daily basis? And
Yeah, so they have
what-
they do the
What do the
gauges.
citizens add with all that?
So they do. So that's where these measurements. So. So these are measurements from like the Coast Guard and the Navy. So these are gauging stations and buoys, right? They can give you broad strokes, but the idea is to actually start thinking about what the interaction is between the tide, which they can predict. I mean, if it was a bathtub, they could predict where it would be on the bathtub, right? Like you could look at this and say, it's going to be 0.4 feet higher, right? But the problem is that when you're looking at, it's not just topography, right? Like it's not just this in a bathtub. It's that you have different porosity of basalt. So you have like places where it might go up further and down further. You have issues with storm drainages. You have the actual buildings themselves. And that's not something that the Coast Guard or anybody is like, it's not their job. Right? So
What's their
I'm not
job?
going to tell you it's going to come up 0.4 feet. On average, it's 0.4 feet, but it turns out over the course of the island, it ends up being really different. And so becomes like the citizen scientists become the intersection between like the science and the management and the policy. It's not so much as the.
But in harbors and shipping channels and things like that, what they have to monitor the height of the water.
Yeah.
In real time.
Yeah, in real time. But they're not doing it, they're not actually doing it in the U-Haul parking lot and figuring out what the interaction is between the shipping lane and like how the water is getting inland. Yeah.
Can you go back just one slide so I can read that?
Yeah.
I
I used to teach this, and I have a good video of it because it actually shows like when the tide comes back on the side, you get your like super big one, but I'm going to zoom through this. I can't show video on everything.
Sarah, would it be fair to say that the internet has really made it is too strong of a term now, but citizen science really requires that global network?
Yeah, I mean these big well, kind of. I think for the newest ones, yes, like these ones, certainly the king tides and the volcano, but the reef watch has been really important. I mean, I won't say it's pre-internet because like it was beginning, right? But they don't actually depend on uploading it to a database. They do now, but most of those, like you might have a global database of fish populations, but a lot of those are local problems, right? So when they're looking at bleaching in different areas, or the Indonesian low, that was really local, and understanding that came from the fact that people really like to dive in Indonesia, and which is great that they are able to leverage that people are interested in that activity while they're on vacation.
Is it the detail informs the generalities that actually are on the larger measurements?
Sorry?
Is it the details that the citizen scientist can provide that
Yeah.
actually informs the larger measurements?
Yeah, definitely. Yeah. I mean, the satellites are very broad. They need ground truthing, but even not, unless you're the Department of Defense, you're not getting down to the centimeter in terms of image, and you're certainly not going to waste, terabytes on a single image of a single coral reef, right? And even going forward, I think that amount of data on something that they need to make generalities of, then the detail from someone on the ground, they can map out, they can interpolate better the details. Does that make sense?
Mhm.
Well, thank you.
Any other questions? A couple things real quick then, sort of the usual, but Bob Smith will be giving a presentation again on basically the plumbing of the water table in 2 weeks. 2 weeks from tomorrow. We usually do Tuesdays. When we do break up, if you would be so kind, just in a second, to help move the chairs to the side again. Sarah, we have just a small token of appreciation for